In this video, we're going to continue our discussion of conservation of momentum in collisions. Specifically, we'll be looking at the fact that collisions can be broken down into two types, elastic and inelastic collisions. So what do we mean by elastic collisions? In an elastic collision, momentum is conserved and kinetic energy is also conserved. Whereas in an inelastic collision, only momentum is conserved. So before we go any further, let's just make sure that this is very clear. Momentum is always conserved in a collision. So don't get confused by that. Momentum is always conserved. So what distinguishes an elastic collision from an inelastic collision is whether the kinetic energy is also conserved. So what we're talking about here is if I add up all of the kinetic energy of my objects before the collision, and I add up all the kinetic energy of the objects after the collision, do I get the same value? Well, if you do, we call that collision elastic. If you don't, it's inelastic. So in an inelastic collision, we end up with less kinetic energy than we started with. And that's not because energy is not conserved. It's just that kinetic energy is not conserved because that energy gets transformed into another type of energy, and usually ultimately thermal energy. The thing to understand about inelastic collisions is that basically it means energy went into deforming the objects. So think about a car crash. That's definitely an inelastic collision because some of the energy that's initially in the form of kinetic energy actually goes into bending the metal of the cars in the collision and ultimately ends up as thermal energy. If the objects stick together after the collision, then we call the collision completely inelastic. It turns out that when the objects stick together, that's when we lose the most kinetic energy. So a completely inelastic collision is simply a subset of inelastic collisions. So again, if the collision is elastic, it means that the kinetic energy is also conserved. In an inelastic collision, we lose kinetic energy because it gets transformed into some other form, ultimately thermal energy. There's a really good simulation on the PhET website, and I strongly recommend that you check it out. What I wanted to just point out to you here is that in that collision simulation, they have a bar that says elasticity on it, and one end is labeled elastic and one end is labeled inelastic. The key thing I want you to understand is if you're anywhere to the left of right here, it's inelastic. And in fact, if you're all the way here, that's completely inelastic. So if we lose any kinetic energy at all, it's inelastic. If the objects stick together, that's when we lose the most kinetic energy, and then it's completely inelastic. Try out that simulation. You'll notice that if I just slide my slider a little bit like to there, you won't really notice just looking at the collision that it's any different, but the kinetic energy after the collision is less than it was before. Let's look at an example. Two objects collide. Object 1 has a mass of 2 kilograms and an initial velocity of 3 meters per second. Object 2 has a mass of 3 kilograms and is initially at rest. The final velocity of object 1 is 1 meter per second. What's the final velocity of object 2, and was the collision elastic? Well, you guys know how to do the first part, definitely. It's just conservation of momentum. So why don't you go ahead and pause the video and find the final velocity of object 2, and then restart the video and just make sure that you got it right and that you wrote it out correctly. Okay, let's go through the conservation of momentum part. We've got object 1. So that's object 1. Here's object 2. Object 1 had an initial velocity, v1 initial, of 3 meters per second. Object 2 had an initial velocity, v2 initial, of 0. So we want to write down conservation of momentum. Remember that we're always going to write capital I is equal to, capital P initial is equal to capital P final. And now we're going to write out what it is. Well, most generally, beforehand, the two objects could each be moving. We'd have m1 v1 initial plus m2 v2 initial. And the same thing could also be true after the collision. So we'd have m1 v1 final plus m2 v2 final. Now, in this particular problem, we're given information that object 2 is initially at rest. So we can get rid of that term. And solving for v2 final, I get m1 v1 initial minus m1 v1 final divided by m2. I'll let you plug in the values. What I got when I did that was I got 1.3 meters per second. So that's the final velocity of object 2. You'll notice it makes sense. It's a positive velocity, so object 2 is moving to the right, as well as object 1 is moving to the right after the collision. So now the next question is, was the collision elastic? Remember that to determine whether a collision is elastic or not, it's all about what's going on with the kinetic energy before and after the collision. So here's how we do it. Here's how we determine whether a collision is elastic or not. The most important thing to understand is you cannot tell by looking. If you look at the collision and you think you're judging whether it's elastic or inelastic, you're not going to get it right. Okay? We have to do the math. The only case where we can know just by looking at it is when the objects stick together, because then we know it's completely inelastic. But if the objects don't stick together, you can't tell by looking. You've got to do the calculation. So what do? We know that if the kinetic energy before and after the collision is the same, the collision is elastic. If the kinetic energy before is greater than the kinetic energy after, then the collision is inelastic. So all we have to do is calculate Ki and Kf. Notice we are not using the work energy principle here. Energy overall is still conserved. We're only focusing on kinetic energy. So let's go ahead and calculate it. So the initial kinetic energy in this problem would be the initial kinetic energy of object 1 plus the initial kinetic energy of object 2. Now in this particular problem, object 2 is at rest, but more generally, both objects could be moving before the collision. So I get 1/2 2 times 3 squared plus 0. If you work that out, you should find that the kinetic energy before the collision, the total kinetic energy, was 9 joules. Now, we've got to do the same thing after the collision. So we want to add up the kinetic energy of each of the objects after the collision. We get 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. We know that object 1 had a final velocity of 1 meter per second, and we determined that object 2 had a final velocity of 1.3 meters per second. So that's the calculation that we need to do. If you go through and calculate this yourself, what you should find is that the final kinetic energy is 3.7 joules. Therefore, since Ki was greater than Kf, the collision is inelastic. Now, the objects didn't stick together, so it's not completely inelastic. It's just inelastic. Kinetic energy was lost. Probably it went into deforming the objects. In other words, they crashed into each other and sustained damage. Now, one of the things about one-dimensional elastic collisions is that if we know the collision is elastic, then we actually have two different things that are being conserved. We know that momentum is conserved and kinetic energy is conserved. Well, as you know, if we have two equations, we should be able to solve for two unknowns. And what that means is if we know the masses of the two objects and we know the two initial velocities, we should be able to solve for both v1 final and v2 final, just in terms of those four initial quantities, because we've got two equations. Two equations can solve for two unknowns. What we're going to do is we're going to go through and derive formulas for v1 final and v2 final in terms of the masses and the initial velocities. This is going to take a few slides. It's not hard algebra, but it's a bunch of algebra. So you might just try it on your own, see how far you can get. The question is, I've got these two equations. I know I should be able to rearrange them so that I get v1 final just in terms of the initial values and v2 final just in terms of the initial values. The way you do this, though, is a little bit, it's a little tricky. So I want to just go through it for you so you can see this kind of manipulation. The first thing that I'm going to do is I'm going to take my momentum equation and I'm going to rewrite it with the m1 terms on the left and the m1 and the m2 terms on the right. So in other words, m1 v1 initial minus m1 v1 final is equal to m2 v2 final minus m2 v2 initial. So I just brought this term over to the left and I brought this term over to the right. The next thing that I'm going to do is I'm going to factor out the m's. So I get m1 times v1 initial minus v1 final is equal to m2 times v2 final minus v2 initial. Now I'm going to do the exact same thing with my kinetic energy equation. The only thing I'm going to do first is I'm going to get rid of the 1/2. So I'm going to multiply through by 2 to get rid of those. So first I'm going to gather the m1 terms on the left. So m1 v1 initial squared minus m1 v1 final squared. And then I'm going to gather the m2 terms on the right. m2 v2 final squared minus m2 v2 initial squared. And then again, I'm going to factor out the m's. So I get m1 v1 initial squared minus v1 final squared is equal to m2 times v2 final squared minus v2 initial squared. Okay. What I now want to do is I want to look at these two equations that I've got. I've got this equation and I've got this equation. And I want to figure out a clever way to combine those. Well, there's a little bit of math that you have to be able to recognize here. What you want to remember from your math education is that a squared minus b squared is equal to a plus b times a minus b. So what I'm going to do is I'm going to rewrite this one more time in the following way. m1 v1 initial minus v1 final times v1 initial plus v1 final is equal to m2 V2 final minus V2 initial times V2 final plus V2 initial. Now I'm going to take this equation and I'm going to take this equation and I'm going to rewrite them on the next slide. So I've written the kinetic energy equation on the top, and then just below it I've written the conservation of momentum equation. And now what I'm going to do is I'm literally going to use that bar on the screen and I'm going to divide both sides of the top equation by both sides of the bottom equation. You'll notice that this will cancel with this, M1 with M1, M2 with M2, V2 final minus V2 initial with that term. And what I'm left with when I divide is I just get V1 initial plus V1 final is equal to V2 initial plus V2 final. That's kind of an interesting result. When the collision is elastic, the sum of the velocities, initial and final, for object 1 is equal to the sum of the velocities, initial and final, for object 2. Certainly not something that I would have come up with off the top of my head, but that's what the math shows us. So we've just found this equation, and this of course is just our regular conservation of momentum equation. It's not a lot more work to get to our final answer. I'm not going to do it for you because you're all capable of doing that algebra. In other words, if you take those two equations, for example, solve this equation for V1 final in terms of the other three terms and then substitute it in here, that will get rid of V1 final, and then solve it for V2 final. That's how you'll get this equation, and then you can do the opposite thing to get this one. So it's worthwhile to just make sure you can do algebra like that. You certainly should be able to at this point in your math careers. But let's look at the results. What we find is if we have a one-dimensional collision and we know that the collision is elastic, we know that the objects aren't getting deformed, there's no kinetic energy lost, then we can determine the final velocity of each of the two objects simply by knowing what their initial velocities were and what their masses were. Now make sure you realize only true for one-dimensional elastic. If on an exam I give you a problem and I don't tell you the collision is elastic, don't use these formulas. You can only use them if you know the collision is elastic. So why do we derive formulas like this? Well, part of the reason we do it is that usually we can gain some insight that we couldn't gain by just plugging in values. And what I want to do is I want to go through three special cases and see what these formulas tell us. In each of the three special cases, object 2 is going to be initially at rest. And therefore, these terms go away. In other words, V2 initial, notice in all three cases, is 0. All right, so the first case I want to look at is object number 1 is much smaller than object number 2. So that notation when we have two less than signs means much, much smaller. So in other words, picture M2 as being like a million and M1 being 1. Picture a tiny object bouncing off a very large object. Well, let's see what these equations predict for V1 final and V2 final. So if we look at this equation for V1 final, if M1 is much less than M2, again, picture that being like 1 and that being a million. We'd have basically 1 minus a million over 1 plus a million. Well, that's basically just 1, right? In the limit that M2 is way bigger than M1, that's going to effectively be insignificant. And so we end up with minus m2 over m2 times v1 initial. In other words, when a very tiny object bounces off a very big object, the tiny object essentially comes back with a final velocity equal to minus its initial velocity. Now, what happens to the final velocity of object number 2? Well, what happens if you take a tiny value, multiply it by 2, and divide by a huge value? Well, if m2 is much, much bigger than m1, effectively it's 0. And that makes sense. If a tiny little object bounces off a really big object, does it change the velocity of the big object noticeably? And the answer is no. So that's one way we can use those formulas. Let's look at another special case. This is one you're going to be familiar with if you've ever played pool. And that is, what if object 2 again is initially at rest and object 1 and object 2 have the same mass? What's going to happen to v1, or what will v1 final be and what will v2 final be? Well, notice if the masses are the same, v1 final is going to be equal to 0. So object 1 is going to hit object 2 and it's just going to stop. Notice v2 final, we get 2m1 over m1 plus m2, but they're the same, so we get 2m1 over 2m1. In other words, v2 final is just going to be the same as v1 initial. And again, if you've ever played pool before, you've seen this, where if you hit another ball directly with the cue ball stops and the second ball goes off essentially with the same velocity that the cue ball had initially. Let's look at one more special case. How about if m1 is much, much bigger than m2 and m2 is initially at rest? Well, this is actually the one that gives a result that is not something I'd ever guessed without looking at the formulas. You know, this case and this case, I think conceptually we can understand. But let's see what our formulas predict when a very big object hits a very small object. So v1 final, you'll notice we've got m2 is now the tiny object. So we have really big minus a small amount, really big plus a small amount. So effectively m2 is insignificant compared to m1, and what we notice is v1 final is just going to be equal to v1 initial. Now that part makes sense. In other words, when a really big object hits a tiny object, the big object doesn't notice any change. It doesn't slow down in any kind of a noticeable way. But let's look at what the velocity of the little object will be. Well, notice here, again, m1 is the very big mass, so we have 2 times the big mass divided by the big mass plus an insignificant amount of mass. And so that fraction just simplifies to 2. And what we find is the little object will have a final velocity equal to twice the initial velocity of object 1. And that's the one that I find is really interesting. Really big object hits a tiny object, the tiny object will go off with twice the velocity of the object that hit it. And I definitely wouldn't have predicted that on my own. Why don't you go ahead and just get some practice with these formulas by doing this problem. A 0.060 kilogram ball moving to the right with a speed of 7 meters per second has a head-on collision with a 0.090 kilogram ball moving to the left with a speed of 3 meters per second. What are the final velocities of the two balls? Assume the collision was elastic. So because we've been told it's elastic, we know that we can use these two formulas. Go ahead, pause the video, plug in, and see what you get. Okay, so plugging in the values, I called M1 the 0.060 kilogram ball and M2 the 0.090 kilogram ball. Now, object 1 is moving to the right with a speed of 7 meters per second, so that's v1 initial. Notice that object 2, its initial velocity is negative 3 meters per second. So I don't know if you noticed, I kind of tried to trick you there. I wanted to make sure you were paying attention when I said moving to the left with a speed of 3 meters per second. So you've got to put in a velocity of negative 3 meters per second. Okay, once you've got that, then it's just a matter of plugging in and calculating. So we've got 0.060 minus 0.090 divided by 0.060 plus 0.090 times 7 plus 2 times 0.090 over 0.060 plus 0.090 times negative 3. When I worked that out, I got negative 5 meters per second for my final velocity of object 1. For object number 2, again, just plugging in the values, I've got 2 times 0.060 divided by 0.060 plus 0.090 times 7 plus 0.090 minus 0.060 times negative 3, again divided by the sum of the two masses. When I calculated that, I got 5 meters per second. Now, by the way, there's a check that you can do to make sure that this makes sense. Remember that we said in a one-dimensional elastic collision, it always has to be true that v1 initial plus v1 final is equal to v2 initial plus v2 final. So you can check and make sure that that's true. You'll notice that if I take 7 minus 5, I get 2. And if I take minus 3 plus 5, I also get 2. And so that's a check that we can do to see that we got the problem right. Okay, in our next video, we're going to look at something called impulse, and we'll also be talking about two-dimensional collisions.